This is chapter 6. We are going to be covering streams first. So I'm sure you know what the water cycle is. Rain or snow falls. It either infiltrates into the ground where it becomes groundwater. If it doesn't, we call that runoff, where it goes into streams. The groundwater can also usually end up in the streams. All that somehow, one way or another, ends up in the ocean. Um, it evaporates if it is breathed out by plants, if you will. That's evapotranspiration. Um, it can also go back into the atmosphere via volcanic gases, where it then precipitates again, and then it can be stored as ice. So, water cycle. Uh, Streams. So, streams are just a flowing channel of water. Rivers tend to be bigger, but it's all a relative term. I've seen streams in Kentucky that California would have called a river. They always flow downhill. Water will always take the path of least resistance, which is towards gravity, and the easiest thing to flow over. Size of the streams are influenced by the size of the drainage basin, which is essentially the bowl that river is collecting water from. So if a drop falls on the land, is it going to come down this bowl or is it going to come down this bowl? Separating the drainage basins, which are also called watersheds, is the drainage divide. So if a drop falls right here, it's going to go this way. If a drop falls right here, it's going to come this way. So this river here has this watershed. These little tributaries that eventually join together and join with the river also have their own watershed. So again, like if it falls here, it's going to flow into this stream. So this stream here has its own little watershed by this drainage divide and this drainage divide. So the bigger the river, the more tributaries it's collecting and the larger its drainage basin is becoming. Obviously, climate influences that. The more water, the bigger the river. The vegetation or the lack thereof affects it as well, and the underlying geology. If you have soils and porous rocks that can kind of soak up that infiltrate, allow more water to infiltrate into the groundwater system, then you may not have as large streams and rivers. If it's very impermeable, you're going to have more runoff that's flowing into these waterways. Let's see, drainage basin, drainage divide. Okay. Oh, and then the map here, I'll go back one. This just shows the Chesapeake Bay watershed. These can be actually quite big. The Mississippi, not shown here, is huge. It's maybe a third of the country. Streams are measured by their discharge. Discharge in equation form, it's written as a Q, and it is the area of the channel times the velocity of the water coming through it. So you do the math, and then that ends up, depending on if this is the velocity is in meters per second or feet per second, you end up discharge is in units of cubic feet or cubic meters per second. Again, it's kind of influenced by the same things that the size of the river is influenced by. So in this example here, you have 25 square meters of your cross-sectional area times 5 meters per second gives you a discharge of 125 cubic meters per second. Load, I've mentioned this before, but here's a definition. So load is the sediments that the river is transporting downstream. Together, we call it load, or I'll say bed load, although I think technically bed load is just the lower material here. The larger materials that are too heavy to float in the water are either rolled or slide. Those are the traction load. Sand grains can kind of get picked up by the current a little bit, but then ultimately they're too heavy. They end up falling back down. And then when it hits another sand grain, this one hits this one, it kind of makes this one bounce. And then it can kind of float for a little bit and then come back down almost like a chicken trying to fly. That is, so saltation is that bouncing of the grains. Traction load are the big gravels and boulders. A suspended load is your clay and silts that float in the water, and then the dissolved loads are ions, so things that have been dissolved in the water, like salt would have, if you have naturally occurring salt in your drainage basin, it's just going to dissolve, and those ions are going to be carried down the watershed towards the ocean. Capacity is a term of how much material is being moved. So discharge is water, capacity, the amount of grains and sediment being moved. Oh, and there's a positive relationship between the two. The larger the discharge, the more capacity it's going to have, and the faster the water, the heavier material it can move. If it's a slow moving stream, it doesn't have the velocity to push these larger pieces, so you're only going to have the silt and clay being transported. You're only going to get, then increase it a little bit more, sand's going to begin to be transported, and then really fast you'll get the boulders and the gravels. And velocity is really determined by the gradient. The gradient is just how steep it is. The faster or the steeper it is, the faster it is, which makes sense. A very steep slide, you're going to go down much faster than like a shallow is not the term. Not so steep slide. We call it the gradient of the stream. It's the same thing as rise over run in math. If you have like a profile and you need to figure that out, it's just, the beginning elevation minus the end elevation divided by the distance. Water distance, water flows faster and steep. Let's see, I'm trying to go through this. And so there's a trend. It's usually, the river is usually steeper up in the mountains, more towards its beginning point. Up in here, it's very steep. And then as it gets towards the bottom, it flattens out. We're going to get into that a little bit more, but up here, where it's very steep, it's flowing really fast, and it has a lot of energy, and the energy is going into down cutting this valley here. So it's forming, we call it a V-shaped valley, because rivers tend to cut V-shaped valley as opposed to glaciers that cut U-shaped valleys that are really broad at the bottom. But it's down cutting, so it's kind of wanting to lower the elevation of this region, and it wants to lower it to the point of its base level, which is where the river or the stream kind of stops flowing and where it ends at either a lake or the ocean. So base level is either the elevation of the lake or its sea level. And so all this up here where it's steeper, it's trying to like down cut and flatten this out. It gets down here, it's going to slow down, and right here, it's going to drop its heavier load. So you're going to get it's dropping its boulders and things here, and then it's going to drop its gravel over here. Maybe it's too slow, it can't carry the sand is dropped, it gets out here, it's really slow, but there's a little bit of motion. Maybe it's dropping its silt, and then when it gets out to the lake or the ocean, the only thing left is clay that eventually will settle out as well. And so because of that trend, we get what we call sorted particles, which might be, it's on the next slide. Let's see. Oh, and this here is just the longitudinal profile, which is like a topographical profile of the stream. So here's well sorted. So in geology, if we have some sediments where they're all pretty much the same size, like if you think of your stereotypical beach where everything is just that sand grain size, that is what we call well sorted. We call it poorly sorted if you have gravels and sands and silts and clays and maybe some boulders. That's poorly sorted. And that all comes down or goes back to the energy in its depositional environment, as I was talking about here. And so you tend to get in rivers this trending of sorting. It's well sorted everywhere along here, but it's coarser deposits all the way to very fine deposits based on the energy of the stream. At the ocean, you'll see sand here at the ocean instead of silts because the ocean waves still have the energy to remove the sand grains. You don't find that so much at lakes. You can, obviously, lakes do have beaches, but it would be the same thing in areas where there's more energy in lake currents. Okay, so where it's dropping, all of that right here, that's silty, clay, maybe sand, depending on exactly the elevation. That is called either a delta or an alluvial fan. So a delta is more fine grained. It is what happens like in this situation where it's had time to slowly drop its heavier things, and by the time it gets to where it's going, it only has the finer particles. So this is a delta. An alluvial fan forms when it's really close to the mountains. So if the hills were right here next to the river, it's going to drop almost everything at the base right here, the gravel, the sand. Then you wouldn't really have a very well sorted environment because it's going from high energy to practically nothing at once. Those are called alluvial fans. This can happen not only in lakes and oceans, but also just at the like when a mountain comes into the valley. And so right there at the base of the mountain, you'll see a lot of alluvial fans. And this is very common out in the basin and range area where you have, basin and range being mountain, valley with very steep faults separating the two. And so the streams come out of those hills and it's like an almost instant drop to flatness. Channel and floodplain. All right, so the energy of the river, when it's steep, it likes to down cut. It's trying to flatten out that elevation. Once it gets to an area where it's already flat, or if it's an old river, then it has kind of done a good job flattening out throughout, thousands of years. Then the energy kind of starts going back and forth instead of down. So when you're up in the mountains in those V-shaped valleys, canyons are much straighter than the rivers are when you get down into the meandering section, the flatter topography. And so the energy then of the river right here, it's like a water slide. Like you're on the water slide and you come around the curve and you go up high, and then the next curve, you go up high on the other side. Where all that energy is on that one side, that is the cut bank. You're eroding the ground right here at the cut bank. On the opposite side, where if you're on that water slide and you're not going up, it's much slower water currents on this side. And so things are being deposited there. This is where we would find those placer materials on these point bars. And so you have erosion, deposition, cut bank, point bar, just based on how that current is flowing. Through time, these change. They like to flatten things out. So eventually, the whole area becomes flatter and flatter and flatter, as well as kind of widening the area out and flattening around. During floods, the river will kind of find little shortcuts to take and will cut off a meander. And when that happens, then you get these little old parts of what was the river that are now disconnected to the river, and we call those oxbow lakes. Eventually, they fill up with sediment and dry up, but they'll stay a little lake for a while, and of course, they can be refilled with water if it's a very humid environment. So the rivers change course throughout time, just naturally, again, because of the path of least resistance. If you have a point bar that is depositing, and cutting, you can imagine it's going to keep doing that further and further and further, larger and larger meanders, until there's a big flood or high energy event where it can kind of take a shortcut and cut cut off one of those curves. Here's an aerial image where that happened. You can see the river was connecting to this other one here via this little lake. And then that was cut off after a storm event where that little area was pretty much abandoned. A floodplain is that flat region or valley floor where the meanders are. Oh, and braided streams. This is, I don't think only associated with glaciers, but like most of them are associated with glaciers. There might be some that aren't. So you'll find this is very poorly sorted environment, a lot of gravels and sands and things here. As the glacier is melting, it's really just meltwater coming out of the glacier. And because the glaciers have a lot of sediment that they picked up when they were growing and moving, that sediment kind of gets washed downstream a little bit too. And so this is kind of like the whole channel, like the whole floodplain of this braided stream, with little individual channels that are constantly changing and going back and forth all the time. The same thing happens with deltas. Deltas like to kind of change all the time too. And that's one of the reasons the Mississippi Delta was hit so badly in that Hurricane Katrina, because we've kind of engineered that river to stop moving. So when we did that, we've also destabilized the delta. All right, and so now we will start on floods.